was just like a talk about policy programming.
Was it David?
Yeah, it was there. And then like at the end, he like kind of mentioned Edward.
Stan is very mature, but has its own problems. So, for example, when it doesn't handle discrete variable well,
Yeah, that's one.
unless you integrate it out, and you cannot always integrate it out. So, for example, if you want to do spine and slab model, it's like, the spine and slab model is like, you can think of it as a mixture of spike and slab. But let's say you have a lot of it, right, on the genome level. So you can integrate out this selector, right, which is like so you can do a spike. But that's fine. You can think of a spike as a Gaussian with very small width. That's fine. But then I haven't been able to get it done. So my feeling is that you still need to know how to write your algorithm well. And then you, at the end of the day, in practice, the way it works is that it has to be some sort of like a combination. By the way, I'm not recognition. Okay, hopefully that doesn't do it. So at the end, you have to use some sort of a mixture of your own algorithm and some of these programming as a soft module. But it's good to know both. You cannot get a brain without knowing what to do with brain. All right, so let's get it started. So today I'm going to talk about mean field. Last time we talked about variational inference, and we mentioned that looping belief propagation under the hood is optimizing the Beth energy function. So today I'm going to give you another variant of the variational optimization, variational approximation, when the form of the queries that you are interested in is not easy to be computed in a closed form or in an exact way. So we mentioned last time that the Beth energy does not give you, so you want to estimate some sort of cost function that's hard to approximate. So Beth energy's idea is that it pretends that the looping graph is a tree, but that approximation is not obvious as a lower bound or upper bound to what you actually want to optimize, but in practice it works pretty well. So today I'm going to talk about mean field approximation, which is another variant. So here we go, this same slide that we always show that gives you an example of the kind of inferential problems that we have to face with in a daily basis using graphical models. So here are some of the examples. So on the top, what I'm showing you is a Bayes rule. I'm just showing that again in order to make sure that all of us are on the same page. Hopefully by now you know that if assuming that y is the data, is your observation, is z is the latent random variables, this is called posterior, this is called likelihood, prior, and evidence, or marginal likelihood. So hopefully by now I've repeated it so many times that you have seen this. And examples of the inferential question or queries that we have from graphical model is computing the probability of the data y, integrating out the random variables, the unknown random variables theta, or computing some sort of expectation of a function, for example f, or predicting predicting the data given whatever you have. So if you are assuming, so t can be a time series or can be, for example, the data that you have observed before, and t plus 1 is something that you want to estimate the probability of integrating out the rest of the variables. So these are the type of questions. So let me ask you one question. So let's say that I want to estimate probability of y being a set of a class, belong to a set A, given x. Can you write it as an expectation for me? Can you write it as this?
Expectation of indicator y.
Exactly. So this is basically writing as an expectation of indicator function that y belongs to A, given x. This is another way of saying the same thing. So the reason I'm telling you this because I want to say that this if you can compute this expectation, is pretty powerful. You can write many of the queries, for example, this marginalization that I showed you as an expectation. So what is variational method? We're going to go to the bottom of this today and maybe the next session, but the general idea is that you have some true posterior probability that can be bimodal, any sort of a crazy shape. You don't know what it is you're interested to compute it, but because you cannot, so because you don't have any closed form for that, you formulate as a sort of like find the closest distribution from a family of the distribution, from the class of the distribution that's parameterized by phi, and you try to find the closest distance between that family and the true distribution. So now, here is a little bit of a loopy argument because you may say that, wait a minute, you want to find the closest distance to what you actually want to compute. You don't know what that is. So how do you want to find the closest distance? If I have it, like I don't need to find another one, right? So I will get to that idea in the following slides, but I want to give you a general idea that we have a set or a family of probability distribution that is, for some reason, it's easy for us. Let's call this curly Q, and Q belongs to that. And for some reason, this curly Q has a nice behavior. It's like I know how to compute the, let's say, entropy of that. It was like I know how to handle it, and I try to find the closest KL distance between that and what I actually am interested in. So in the following, I'm going to tell you how we actually do this. So what do we call it variational? What does it mean variational? So let me give you again very 2 seconds introduction of the variational calculus. It's much bigger than that, but it's good enough 2 seconds introduction to variational calculus. So what is the difference between calculus of multivariate and variational calculus? So let me give you a notion of the function. So the function, as all of you guys know from your high school math, is that you provided a multivariate variable argument, and it spits out a number for you. So an example of that is, for example, when you want to compute a maximum likelihood for a probability distribution that is parameterized by theta. So this is a parameter, you know the form of this guy, and you want to find the best theta to optimize it. So Px given theta is a function. Theta is a parameter, like a multivariate, and you differentiate it with respect to theta, set it 0, there you go. You have your maximum likelihood estimation. So that is the notion of the function. So we also have a notion of functional. So the functional, you can think of it as, instead of accepting one set of variables, like 10 variables, which is your theta, it accepts a function and it spits out the number for you. So that is the difference between function and functional. Like, don't repeat that again in front of your friends that have taken measure theory. I'm putting so many things on the rock, but this is good enough for going quickly over that. So, but anyway, what are the examples of the functionals? Entropy is a functional. The argument to that would be probability distribution. Output would be entropy. Input is a function, which is your density. Output would be your entropy. So this is the definition of the functional. So what is that good for? Well, we can do the same things that we do for the functions, make a derivative and all of that, with respect to functions. So you can make a derivative with respect to theta, that is your parameter. So here you can make a derivative with respect to function. So here are some 2 very basic rules that you can use to make a derivative of the function. So these are 2 rules. So basically the first rule says that, so instead of using partial of the functional with respect to function, we use delta to indicate the function. So if I make a derivative of f with respect to f, but with a different argument, So the result would be a delta function. Everybody knows delta function. Who doesn't know delta function? I'll explain it one second. Okay, so delta function is basically a function that's zero everywhere except when the argument becomes zero. And the argument becomes zero. And in that location, the value is infinity, but the infinity that's integrable. So it means that, oops. Why is not working? Okay, it's working. So is the delta at zero? So people usually use it as a delta or spike, but the integral of delta x is 1 dx. So you can think of it as a function that has value only on a measure zero or location, but is integrable. Okay, so these are two rules. So if you want to make a derivative of the function with respect to itself, but with a different argument, the result is delta. And if you want to make a derivative with respect to, so the idea here is that this is a normal derivative that you're familiar with, and this is the delta derivative. So let me apply it in a context, and then you'll see that. So I told you that entropy is an example of the functional. So of course, Px should belong to the family of the density function. This is not every function because it has to be proper density, it has to integrate to 1. So how can I compute the maximum entropy probability? So remember the definition of the entropy. So now I'm going to apply those two rules on entropy and tell you what's a functional derivative of entropy. So remember the first rule. So I want to make a derivative, delta, with respect to Px. So this is my function. So first, I'm going to pretend P is just a parameter. So I'm going to switch the order of gradient taker with the integral. You can't always do that, but don't tell your mathematician friends. So the first one would be applying, so pretend that theta is just a parameter. It's not a function, it's just a parameter. Derivative of, so it's going to be derivative of this guy plus derivative of this guy, right? So the derivative of this guy is going to be just, it's just the derivative of P with respect to P is going to be nothing, but except that because it's inside of integral, you have to, using this rule, you have to put a delta function. And derivative of this guy is going to be 1 over Px, but because the argument is variable, you have to put a delta function. Right? Yes?
Up there, are those on the left side partial derivatives or delta functions?
Which one?
Up left.
This?
Fx over fx prime. Yeah, those two.
These are delta, which I use delta to indicate that I'm taking derivative of the two functions. So I'm saying that if I take a derivative of a function, so function is an argument, right? So remember that when you're using your daily basis, calculus, you have a function of theta, right? You can say that partial of f with respect to theta. Now theta can now be a function. So now we can say delta f with respect to anything that you want, right? So I'm going to do delta f with respect to delta f, except that the first one has x, the second one has x prime. Then in that case, the result is delta, which is this rule. Okay, so now I told you that theta x integrates to 1. These two cancel out. This is also delta 1. So what is the result of this? Log p of x. So you're taking integration with respect to x prime. Delta says that everywhere is 0 except that where it is x. So I just have to plug that in. And the first one? 1. So the delta of an entropy, so functional derivative of the entropy would be 1 minus log p. So remember when you were making the derivative of the function, the result, if your parameters are vector, the output would be a vector. When you are taking derivative of a functional, the output would be function, which is function. Anyway, we're going to use this later on. So The reason it is called variational approximation because we are using calculus of the variation. So what is the goal? Our goal is to compute a form of a difficult distribution such as this that I'm showing here. I have some evidence that I showed you as x, as E, and I want to compute some sort of like a posterior or some marginalization. But it's hard to compute in a closed form, so I'm going to formulate a new distribution called Qx that belongs to a family of distributions that are well behaved or I'm familiar with it or just whatever, that is easy to compute. And then I'm going to find the closest distance between Q and PE. That's the general idea. So what I'm going to use as a distance is very natural to use KL distance. I think last time somebody asked me that, well, KL has some sort of like a funny properties. It's not symmetric. It doesn't satisfy the triangle inequality, and all of this. Why should we use this? The reason that is that KL is very nice, has very nice behavior whenever you don't have the P, when you don't have the P, but you only have it up to a normalization. That is the case here, that I'm going to show you later on. Anyway, so let's take use a KL distance between P that you are interested in and Q which you're approximating.
So E is the two parameter, P, X given E.
So E is your evidence, your data, and X is your random variables. So it's like you can think of it as a posterior. So this is, you can think of it as a data that you have, and this is unknown random variable that you want to compute the posterior with respect to. This is an example of that. But all of them, most of them shows up as form like this. So what does KL means intuitively? You can think of it as an extra bits or called nats that is required to explain PX. If we don't need any extra bits, we're going to match. But if the family that you search within or the queue, your queue is far enough, it means that how many bits you still need to explain your desired PX given E. So, as I mentioned last time, KL, although it's very nice in terms of like the behaviors, but it has some sort of like funny properties. It's asymmetric. We're going to get to the asymmetry of KL in the following slide. It's always non-negative. When you set P and Q equal to each other, the KL becomes 0. Now, so I told you, so we mentioned that like we are interested in computing P X given E, but we don't have it. If we had it, like we didn't need to find another things to optimize. But most of the cases, although we don't have PXE, because of the model, so let's apply the Bayes rule on this. So, right? So this is the joint distribution that we can read from our model. You are given a graphical model. This is your evidence or your data. And X is your latent random variable. You can easily write your joint distribution. The problem, what is the problem here? Yes, exactly. Computing the denominator is difficult because you have to compute this. And computing this integral is hard. So, but at the end of the day, you can think of it, it's just a number with respect to, it doesn't change with respect to X, right? It's just a number. So you can think of this as PXE is proportional to PXE. Or what, to you know, as a shorthand, I can use it as P tilde X. Is a shorthand notation that I'm going to use. So basically, PXE is this P tilde X divided by some normalizer. So I can easily compute P tilde X, but I don't know how to normalize. So let's go with unnormalized version. Okay, so let me expand the KL. So I'm gonna write QX. As I told you, I'm just gonna substitute that in. And as a shorthand, because I don't want to keep repeating px given a, I'm just going to use px. It is not a prior or anything, but it's easier for me to write. Okay, so it's just a substitution. So far, nothing confusing. But then I can expand it, right? Log goes outside, and now this also goes outside of the qx, because this is not a function of x, and this is a proper density. So expectation of a constant is a constant. So I ended up with a KL divergence between the P that I wanted to compute. It was basically, remember, it was a shorthand for Px given E, and a normalizer. Right? So computing this distance with respect to unnormalized version is as if I'm computing the KL distance with the normalized one plus a log partition function. And the beauty of this is that although I don't know how to compute this, I know how to compute this guy. Yes?
So I'm not following. After you wrote P of x given E as P of x, and then down there, like the P tilde.
So from this point out, pretend that Px is Px given E.
What about P tilde x?
P tilde x is the joint distribution, one time, right? It's I wrote it explicit. I'm going to use this shorthand. Okay? So let's say that, so basically what I'm telling you is that, let's say that I have a normalized, I want to compute the KL distance between a probability distribution that for which I don't know the normalizer. That's basically what it boils down. Which in this case is Px. I don't know the normalizer. For the unnormalized version, I'm going to use P tilde. So what I'm telling you is that I don't know how to compute this, but I know how to compute the one on the top, because Q is a distribution that I'm familiar with, I'm comfortable with, or I know how it behaves, whatever. I'm easy to compute. P tilde I can evaluate. I don't know how to normalize, but I can evaluate. So I can compute the expression on the top. And the relationship between expression on the top and expression on the bottom is just a constant. That is, constant is a log partition function. Is this clear? This is probably the gist of idea in variational inference algorithm. If this is not clear, just stop now, because after that we're going to speed up. Clear? Okay. So this is basically the cost function that we are always working with in variational inference. So the first term is a non-negative function. Remember, KL was non-negative. So, and a Jx was this expression, right? This expression on the top. So because you are adding a non-negative function to log partition function, what is the relationship between Jq and KL of Q given P? Which one is bigger, which one is smaller? Oh, sorry. I should say minus log partition function. I need to add a positive number to,
So this is a joint distribution, so it's between 0 and 1. So minus log z would be positive.
Now, okay, so let me ask my question. So which of these two are correct? This or this? You have Jx on the left. I have a non-negative number that's added to get to log x. Right? You need to add a non-negative number to log z to become Jx. So that must be smaller. Okay. So, or you can think of, write it as another way. Remember, z was the normalizer, and this is the what is called elbow. I'll We will explain it later. But you can think of this minus jx as a lower bound for log x. So let's repeat that again. Remember, we wanted to compute this posterior. So we said that let's find a family of distribution curly Q that is easy to compute, and compute the closest member of that family. So this is the family of the curly Q, and this is the member of that Q. And this is what we are actually wanted to optimize. So let me find the closest distance between these two. So this is going to be KL between Q and this P Z given D, right? So we want to compute that. But because we didn't have the normalizer, we expanded, and we ended up with the following equations, which is what I told you at the beginning. What is the first term? Negative entropy. So the first term is negative entropy, and the second term is expectation of your posterior that you don't have access to with respect to Q. We expanded it using Bayes' rule. Basically, we wrote this as PZD PD, right? So it gives this equation for us. But because log PD was constant with respect to Z, it get out of the expectation. So we ended up with this equation, which was what I showed you last time as a J. So this, the negative of that is called elbow. Evidence, because this is called evidence, lower bound. And that is basically the cost function used in variational optimization. It's like basically a negative of this term. It's basically the previous slide. I just like repeated again in different language. Clear? Okay, so what does it mean? Remember, we were interested in computing this KL, but it was hard because I was not able to compute this normalization. Clearly, these are my data. So instead, I'm going to optimize elbow, and by pushing elbow up, I'm reducing this distance, because upper bounded by this evidence lower bound. So that's the general idea of computing this KL that I couldn't compute. Instead, I optimized, basically maximize this elbow to push this boundary. That's the general idea. The idea clear? Okay. So what are the alternative views of the variational inference? So this was our original cost function for unnormalized probability distribution. I expanded, it become sum of two terms, negative entropy plus, because P tilde x is just a normalized function, and log of that can be anything, right? It's just, so remember, P tilde x divided by z was px. So all px needs is just this, right? Any function can be p tilde. So the log of that can be anything. So one way to view that is we can view this optimization as, so remember that we have to minimize JQ, or another way, we want to maximize the negative of this guy. So you want to if you want to minimize this or maximize the negative of that, is as if that you are minimizing this energy while maximizing the entropy. That's one view of variational inference. So these terms called Helmholtz free energy. Helmholtz free energy. Clear?
Can you explain how you got the second one?
Yeah. So this is basically the Q that so it's easy for me, right? Right. So P tilde x was my unnormalized distribution. So what I wrote here is basically the repetition of what I wrote in the previous slide. I'm just repeating and rearranging the terms. So I'm not doing anything fancy here. So I'm just expanding. So this is the log of this is the log of the denominator versus the log of the denominator, right? So this is the log of the numerator minus the log of the denominator. And I told you that PT legs is just a non-negative function. It can be anything, right? As long as it's non-negative, you're fine. Okay, so the log of that is any value because it's unrated. You can think of this as energy. You want to minimize this, or another, so you want to minimize JQ, or another way of saying that you want to maximize minus JQ. Another way of saying that. So if you want to maximize that, it's as if that you want to maximize entropy minus, yeah, it's energy. You want to reduce this energy while entropy is expanding. So you can think of entropy as a regularizer for that energy. That's one view of that. Another view is the KL. Another is basically viewing this as a lower bound. So the same thing that I told you last time, that, well, PD was my normalizer. Remember that my P tilde X was like this. I'm just expanding that. So if I view that as posterior probability, P tilde is my evidence. And if I expand it, what I'm going to get, I get a KL and evidence minus log partition function. This is exactly the same view that I told you here in this slide. Just what I want to say that you can view this as energy, or you can view this as a lower bound idea. So this slide, basically, I'm showing you the lower bound idea. I want to compute this KL between Q and P, but that was hard to compute. Instead, I'm going to maximize this elbow, which is minus JQ. And the entire thing is evidence lower bound. These are two views toward the same approach. Okay, so, but I told you that, so there was something that I did, and nobody asked question that, well, when you write KL like this. So Q of P that you wanted to compute, and you wrote it as an expectation with respect to Q log of this QP. What about other way? What would happen? Why did you choose this order? Why not using KL of P versus Q? Right? Why this specification, not that one? So, and I told you that KL is not symmetric. KL of PQ is not the same as KL of QP. So now suppose that I want to do reverse direction. Instead of using the KL of QP that I used earlier, I choose to use the reverse direction, which is PQ, which has the following form. It's just order of P and Q is reversed. The problem here is that P was what I wanted to compute, but I couldn't. So if I view that, so remember that I know P up to a normalizer most of the time, but I don't know how to sample from it. So if I write this, I can write it as an expectation, right? How can I write it as an expectation, by the way? Exactly. So law of P of X, Q of X. And X is drawn from P of X. So I have two problems. First of all, I don't know the form of P. I know it up to a constant, but I don't know. Also, I don't know how to optimize, how to sample from it. While on the other side, because Q is some sort of like easy distribution or some nice behaved distribution, I know how to sample from it. And all I have to solve is taking care of the fact that my P was unnormalized version, which I did in the previous slide. So that is the difference between them, that one side is harder than the other one. Because most of the time, you don't know how to sample from P. If you knew, you're as if like, you don't need anything. That's the whole idea of the sampling approach. That give me a procedure that I can sample from posterior, and then I can almost answer all of the queries. I can give you an answer to your posterior mean, posterior variance, all of this. You can sample from it an average. So the problem here is that we only know it up to a normalizer. So that causes a problem. So this is why the other side is difficult. So this is why we use the reverse direction that takes an optimization, take an expectation with respect to Q. But for a second, let's assume that both P and Qs are easy. Let's study the behavior of optimizing KL or reverse KL. So let's for a second that my goal here is my goal on this side is optimizing KL with respect to Q. And let's say that for a second, I know what the P is a lame problem. I just want to study the behavior of the KL and reverse KL. So let's for a second assume that computing, I know the form of Px, I know how to evaluate it, and I know how to sample from it. So let's study that. So one side, that is the side that we always use, which is this side, is called information projection. This is basically, our goal is to take an expectation with respect to Q for a log of the Q given divided by Px. This is called information projection. The other side is moment projection. It's called moment projection. So each side has its own interesting properties. For example, for information projection, we know that if you want to minimize this KL distance, if Px is equal to 0, Qx must be strictly bigger than 0. Right? Because if Px, because you want to make sure that this function is defined, right? If this goes to 0, and this goes to 0 too, then you have 0 divided by 0. So what is the side effect of this? The side effect is that if Px is 0, it enforces Qx to be 0. So you can think of it is that if Px is 0, Qx is definitely 0, but not the other way around. So what does it say about the areas that Px is 0 versus areas that Qx is 0? So I said wherever, so let's define two sets. A set is defined as the x's where Px is equal to 0. And B is defined as a set that Qx is divided by 0. Do you think that A is a subset of B or B is a subset of A? So when Px is 0, Qx is definitely 0. So A should be other way around, no? So yeah, so because you want to enforce that whenever A is 0, the other side has to be 0. So the other way around is not correct. So that basically enforces that if you optimize this cost function, that means that it's 0 forcing if you're optimizing with respect to Q. And it's basically everywhere that Q gets to 0, it pushes 0. Whenever P is getting close to 0 in terms of density, it pushes Q to 0. So that results in a distribution that are sharper than P. The side effect of that is that it is going to underestimate the variance of the P because it's sharper. For the other way around, it has other way behavior. So when Qx is equal to 0, Px is equal to 0. So it's going to overestimate the P. So that means that if P has a distribution, so if P looks like this, the Q, so if this is P, the Q is going to be broader. Yes.
Would there, if B would be a subset of A, that means there exists a point that P of X is 0, but Q of X is not.
I mean, just follow this, right? If Px is 0, Qs must be 0. What does it imply? So now, let's see that in the example. Let's say that I have a P, which is a green distribution, it's an ellipsoid distribution. And I'm going to force my Q to be set of probability distribution that only are allowed to have circular distribution. So let me say that I design my Q so that it looks like normal distribution of this. It's always ellipsoid. It's always circular, right? And this is my P that I'm interested in, and this is the family of the Qs. And for a second, let's assume that the mean of both of them is half-half. I know the mean. If I optimize this KL, which is information projection, it's going to underestimate the variance. So it's going to get the center right, but it's going to be included inside of that because it's zero forcing. While if I optimize in the other one, it's going to be broader. So this is my optimal Q star, and this is my Q star here. And that's a behavior that you see in optimizing one KL versus the other.
From a practical consideration, this can also be thought of a precision recall problem, right?
I don't know how.
So if you optimize it the other way, you'll get more points which your model will feel as lie on the distribution, but it's also going to tend to make more mistakes.
Well, so here's my question. So if you want to view it as a precision recall, what is your ground truth? The ground truth is like, how do you define it as a ground truth? So let's say the vanilla version of the precision recall, I have a detection problem. I have a true value to detect, and I have a detector, right? So I have a threshold in my detector says that either I can be very conservative and detect a subset of what the truths are, or I can be very liberal and increase the threshold and recover all of it with the expense of high false positive. So in that case, tell me what's the truth? So the true, what's the ground truth here? The ground truth is so one way probably would be to view the ground truth as a support of the PX. So wherever that's 0, wherever it's non-zero. In reality, what we have here is that most of the probability distribution that we have are not exactly zeros. So they're not. So you can't really. So the support is everywhere of their domain. They may get very small values, but it's not really 0. So the support support for both of them would be entire sets. So it's hard to view that as. But if you define it as, for example, so instead of setting you can define it as a level set. You can say that it's not all of the sets that are equal to 0. It's all of the sets that are bigger than the threshold. Yes. So then. Okay, so what would happen if I applied a mixture of distribution? So let's say that my P, the blue, are a mixture of two distributions, and I'm forcing my Q to be in a family of unimodal distribution. So this is going to be a normal with mean and variance. So we already know that my Q, the set of sets, set of my distribution are handicapped because my true distribution is bimodal. The space that I'm searching within is unimodal, so I won't be able to catch both of them anyway. So there's only one mode in normal Gaussian distribution. So if you optimize the information projection, it's going to have two local minimum. Either it's going to latch to this mode, or going to latch to the other one. And it's going to underestimate. It's going to be a sharper distribution. Because remember, it was zero forcing. While if you optimize the other cost function, it's going to fit one gigantic Gaussian distribution that covers both of the modes. It doesn't know how to break the modes. So it said, I only have one mode. I'm going to make the variance so big that it's going to cover both of them. And that is the behavior that you see in mean field algorithm that basically optimize this one. It's going to latch in, if your posterior probability is bimodal, it's going to latch to one of them. Depends on initialization.
You can make your family distributions also bimodal.
That's right, that's right. Now this is just for the sake of example. This is for the sake of example that I wanted to give you an example that if the class of your approximation is not rich enough, that cannot accommodate the probability distributions that are bimodal, that's the behavior that you want. That in reality, actually, it can happen. So an example that I gave at the beginning about spike and a slap, it's just so you can make your class richer, but if the number of random variables that you want to estimate is big, you have to make a trade-off between computation and the rich family. So then that's your choice. So let's apply this in a context. So remember, I think I've already said that in expectation maximization class. Remember the Jensen inequality, right? So we had the concave function. F was concave function. If I switched the order of F and E, I'm going to introduce inequality, right? So hopefully you guys all remember that from that class. So let's say that I'm interested in, so in this case, if G is a distribution, if I'm interested in computing expectation, if P is a distribution, I'm interested in computing the log of this function G x when x coming from P. If I change the order of the expectation, what is the expectation? Expectation and log, I'm going to get inequality because of the Jensen inequality. So it's going to be expectation of log of gx. So let's say that you are interested in computing this marginal probability distribution. So it's a py. So you have to integrate out all of these latent random variables that are z. That z does not have to be 1. I'm just saying that let's lump all of your latent random variables into z and integrate them. So if you want to compute this log p, so if y is your data, again, what is log p? What is p if y is your data? Huh? What? Yeah, well, marginal likelihood. Because you're marginalizing out anything that's not there. But also it's called evidence, right? Remember, in the context of posterior, I want to compute pyz. This was likelihood prior evidence or marginal likelihood. Okay, if I want to compute that, all I need to do is that I can write this, I can basically multiply and divide it by q. I haven't done anything. So this expectation with respect to q, I just divide and multiply with respect to q. And now I can think of this as a g, as a function, and view this as expectation with respect to q, not p. And that's a trick that we use all the time. And I'm just basically telling you all of these stories that I told you about variational lower bound from different point of view. So all I need to do is that I can write as an expectation of the G with respect to Q. This is my G. But this time, my Z is coming from Q. Here, this was expectation of P by Z, which was my likelihood, when Z is coming from PZ. So I switch the P and Q without any change here between these two equations. Now, if I want to compute the log of that, I can switch the order of log, and because of the Jensen inequality, I'm going to get this. Where the first one is the log of the likelihood with respect to Q, and the other one is the distance between QZ and my prior. So what I'm doing here is that I'm just reintroducing elbow by just reshuffling the terms. I'm just getting the elbow term that I showed you at the beginning of the slide, but rederiving it using Jensen inequality. It's basically the same thing yet again. So the first term is my likelihood random variables, but this time expectation with respect to Q. The first term is the distance between the family of the distribution and my prior. So this is, here we go. So we get the elbow term that we got last time again. So the first term, so here my Y is my data. Q is the family of my probability distribution that I want to optimize. And this term is also called reconstruction term. This is expectation of my likelihood with respect to a Q. And the second one is basically my KL distance. So remember that remember the lower bound. So remember that this graph that I showed you at the beginning, that we were interested in computing this KL, but we couldn't compute it, so we maximize this elbow. If I maximize this elbow, this is elbow, right? This is elbow. It's as if I want to maximize elbow or minimize this minus of this cost function, the same thing. So I want to reduce the reconstruction error while keeping the distance between my Q and my prior. This is exactly the same thing that I told you earlier from different points of view. So you can think of the second term as a penalty. So you are saying basically this. Give me a family of distribution Q, that Q belongs to curly Q, and this is the posterior that you are interested to compute, right? So find the closest distance. Another way of saying this is find the probability of distribution QZ that produce the best reconstruction error. If I sample from Z, plug that into my likelihood, it gives me the best reconstruction. But I don't want to go too far from my prior. So can anybody tell me that what would happen if I only maximize this? If I only maximize this or minimize this energy cost function, that's the same thing, right? Without this term, what would happen? If I only focus on reconstruction without the penalty.
I think it will overfit.
Yes. So that's exactly true. Can you elaborate a little bit on that? So how does it overfit? It's because right now you have a Q that's trying to focus on something that tries to, I only want to have the best reconstruction. I can be as far as, because I don't have the second term, I can be as far as the prior as I want. And you are right, it's going to result in overfitting. But in terms of Q, how does the shape look like? Anybody has intuition? How does the shape going to look like?
So it's probably average.
It either may have a, so it's going to, well, yes, sometimes it's correct. So it's going to, it depends on your model. Yeah, you're right. So you're going to produce something which is like super overconfident. So it says that I'm going to get these points and set a Z to something. Either I'm going to choose, if your model is non-parametric, which means that it grows with your sample size. I'm going to choose all of the points as my observation. Or if I only have access to one parameter, I'm going to make it very picky. So the second term, although it's basically resulted as like reshuffling the term, like we didn't add it as an ad hoc term, you can view it as a regularizer that avoids overfitting. So at the end of the day, we want to optimize this elbow. We want to maximize this elbow to close that KL distance. So, but there is something interesting happening here. So remember at the beginning of this of the talk, we were interested in computing Px given E. So some sort of like a posterior distribution given the data. But we basically recast the problem, change the problem from marginalization to optimization. So the take-home message from this is that we managed to change the marginalization and solve equivalent optimization, saying that if you manage to solve this optimization, you solve that marginalization. And the reason it's important is that our arsenal in optimization is very rich. We know a lot about there are a lot that we don't know, but the tools that we have in optimization is very rich. So if we can change this problem into an optimization, the integration that we don't know how to solve it, into optimization, you can deploy a lot of tools. And it's very scalable. It results in something that's very scalable. We can also have a leverage. We can also have it as a certificate for the convergence, because, well, for example, if your problem ends up being convex, you have a KKT certificate that you can check and know that, well, this is converging. If your problem is non-convex, at least you can monitor the behavior of the cost function and say that, well, it seems that at least it's reaching to some local minimum. So it gives us a way to assess, to evaluate the behavior of our approximation. So now, another interesting thing is that, so far I haven't tell you how we actually optimize this. I just gave you, I don't know, 4 different versions of deriving elbow from different angles, using KL, reversing the direction of KL, using Jensen inequality, they all end up in the same place, and different point of view. I haven't told you how we are going to actually optimize this cost function. And this is what I'm going to talk in the following slides. So the next thing is that, okay, so we are convinced. So this is the cost function that we have to maximize. This is the elbow that we have to maximize. How can I formulate Q? How can I actually maximize this cost function? So overall, there are 2 schools of thought in variational optimization. One of them, so you can divide it into free-form optimization and fixed-form optimization. So during this class, we're only going to cover fixed form, but recently, the progress in deep learning has helped us to go to also free-form optimization, but we are not going to cover it in this class. So what do I mean by free-form? Remember that we were interested in optimizing, we wanted to optimize Px, but we didn't have access to it. But we had access to some sort of like a P x tilde z, right? So what would happen if I view this problem in the most general case by saying that I'm not willing to parameterize Q, I just view it as free function that only constraint that it has is that it has to be a proper density. Proper density means that if I integrate Q over X, sum to 1, and Qx should be this, that's all, right? So what would happen if I just write as a constraint? Should be proper, cost function, should be non-negative. And all I want to do is that elbow cost function, and I'm going to set the derivative, make a derivative and set it to 0. What I'll end up with, I'm going to end up with a form that looks like this. That is the log of my y given z, which is my latent variable and parameters, exponentiated multiplied by px. The problem with this is that you only get the q up to normalizer. If we knew how to compute this normalizer, we didn't need to go to all of this trouble. So finding this normalizer here is as hard as our original problem. So in this class, I'm going to skip the freeform and only talk about that should be fixed form. Sorry. Fixed form.
What is the theta in the equation?
What?
For the freeform, what is the theta inside log of?
Okay. So yeah, it's a good point. So many of the cases in practice, you are interested to compute some sort of inference to some sort of a posterior, but your model may also have parameters. So you design a model that you only know the structure of your model, but you don't know the inside parameter. So by theta, I'm using basically the parameter that you have to optimize. So you basically have two kinds of parameters: parameter of the model and parameters of the approximate inference. So I'm going to talk about it in the next class. But you have two parameters: theta, which is parameter of your model that you want to optimize, and phi, which is parameter of your approximate posterior.
Can you elaborate just a bit about why you said deep learning helps there? Because we are in a non-parametric setting, and neural nets have like finite number of parameters. So I don't understand how they are able to estimate like infinite dimensional.
So it's so I don't want to go into too much detail, but one way of viewing this is, remember when I write the cost function, it looked like something like this, that we had the elbow that looks like a reconstruction error. And some sort of like a KL between Q and PZ. This was our prior, this was our posterior, right? So this was a reconstruction error, right? So I think that back then was PZ, theta, all that, right? Okay. So this was reconstruction, and this was the distance from prior. I'm maximizing elbow or minimizing the negative of this cost function. So one way of viewing that is, so let's say that I want to, because it intuitively makes more sense to me, let me make this negative and this and maximize with respect to that, right? Okay. So what I'm saying is that I have a prior and I want to have a reconstruction, but it shouldn't be too far from prior. So now let's think of it as, what if I have a way to deform my prior so that it produces best reconstruction. Now, one of the ways to view this is to view it as a deformation or as a flow. So, well, if you view it as a deformation, as a flow, you're fitting a function, and the deep learning can help you to fit that function. So let me stop there. Not to go beyond that, but you can view it as a deformation. So you're not explicitly parameterizing; you're only parameterizing the deforming, and that's why it's in some sense quite liberating. But deep learning is still parameter. It's not non-parametric. You have a finite number of parameters, and at least the vanilla version of that, the number of parameters does not grow with your data. Hence, you cannot call it non-parametric. Yes.
So we always assume that true posterior is continuous, right? So that
Good point. So in this setting, we are assuming that like everybody's behaving nice, differentiable, all that. So if there are some discontinuities, so many of the things that I did were switching expectation and integral, things start falling apart. But most of the problem that we have is things are discontinuous. It doesn't mean that all of your random variables is continuous. That's not what I'm saying. You can have a discrete random variable, but the parameters that I have is phi in freeform. I'm just assuming that with respect to phi, things are nice. Because in the entire procedure, I have an elbow, and I have to take a derivative with respect to this phi. And I should be able to switch takes E expectation and gradient, so I'm presuming that I can do it. Yeah. Okay, so compared to that free form, you also have a fixed form. So fixed form says that, okay, give me a form of Q's that's all for different, so basically Q, curly Q that small q belongs to, is a space of all different variant of phi. So for, let's say, for phi 1, this is going to be Q phi 1, this is going to be Q phi 2, and so on and so forth, right? So I'm assuming that, what if I can find a parameterization space? By changing this parameter, I'm just parameterizing the math view. So that is called free form. So what kind of fixed form? So what do I mean? So what is the procedure for to doing variational inference there? So I wrote on it. So this is it. So we are assuming that our class is rich enough. So I have to say that we usually assume that it's rich enough and it's convenient. Because if it is rich enough and you cannot do this expectation, entropy, you're in the same place. It's rich enough, but not so far from the convenience. So you find a class, and you will see that for some of the distribution, this rich family is not hard to find. And we can easily parameterize this. But the general idea is that we find a family of distribution curly Q, which is basically parameterized by phi, and I'm going to change phi so that this KL divergence or elbow is maximized. So that will bring me to the idea of so-called mean field approach. So one of the ways to parameterize, so remember that I lumped in all of my latent random variables, all of unobserved random variables into X. Doesn't mean that X is univariate. It can be, so basically I'm assuming that given a graphical model, this X represents a set of all unobserved random variables in your graphical model. So the idea of the mean field, or I have to say naive mean field, is to assume that this Q is fully decomposable. So what do I mean by that? So let's assume for a second that the probability distribution that you originally had was this kind of like a Markov random field that random variables were in the grid. The approximation that I have is going to cut all of this. So I'm going to assume that I'm going to search within the space of the classes that there is no interaction between them, just because it's convenient. So this is basically the story of mean fields. So basically mean fields, by assuming this fully decomposability, you're basically cutting some of the edges in approximate class. Remember, in your original class, things are still related, but you are, as I said, you have to parameterize your curly Q so that this curly Q is easy to compute. And one of the ways to do that is to cut all of these edges. Then you have set of independent Qs. So we're going to work out some examples to see how does this provide convenience. So our goal is to compute this KL, but because we couldn't exactly optimize it, instead we optimized this elbow cost function, which was a lower bound to the marginal likelihood or evidence. So that was our goal. Now, let's work it out. So remember, so our cost function was expectation of log of, so we want to maximize this, right? We want to maximize this. Px, Qx that here x is coming from q. And we want to maximize this. Right? This is our elbow cost function, what I'm showing here. Now, let's expand that term. And remember that we have this assumption here. We are assuming that q's are fully decomposable. So my q can be written as a bunch of multiplication. So it's basically, I'm saying that it's q1, x1, phi1, q2, x2, phi2, and so on and so forth. All right, so if I expand that as a cost function, so I'm going to write it as, this is my q of x. This is my unnormalized probability distribution. And this was my denominator. Right? Because I didn't do anything, I just had this previous term, I just expanded. Clear so far? Okay. Now, let's for a second assume that I want to maximize it with respect to, I want to maximize this cost function. So let's, given that these q's, each of them has its own parameter, let's fix the rest of the parameter and only focus on qj. Right? The rest are the same. I'm going to only focus on qj. So all I need to do here is that this is just multiplication of a bunch of terms. I'm going to take the qj out and keep the rest of them. And similarly for summation, I'm going to say that I'm going to write this qj as summing over the rest of the random variables and keeping qj out. This is basically, from here to here is just like reordering the term, nothing else. This part clear? Okay. Now, because this term doesn't have any q, so by the way, when I write q minus j, I mean that all of the others except j. That's just easier to write. That's an easy notation. Okay, so this qj has nothing to do with q minus j. I can take this out and expand this. So I'm going to take this. So I'm going to expand the first term by taking qj out and bring this qj in. This is my first term. And similarly for the second term, qj out, second term, and so on. And also remember, and I can bring this qj in, and because all of these q's are decomposable, so I can write this as log qj xj sum over k naught j log qk. Right? Okay. I just rewrote that. Right? So this is the second term that I have. Now, what I'm going to have is basically the following term. This term is basically, I just write it as a log f because it's easier to write. I just say that this is an expectation with respect to qj of some function. I'm going to write it as a log of some function. Doesn't matter, right? And qj, so for this term, this is an expectation with respect to the entire term, right? So there is no qj here, right? There is no qj. There is no qj here. And this is an expectation with respect to qj. So it's going to be a constant. So it goes out of the expectation. So I'm going to end up with this term, which is my second term. And this term, which is my first term. And some sort of a constant, which is expectation with respect to that. There's no qj here, right? There's no qj. So by the way, I can write this as an expectation of, I can write as an expectation of q. So remember, I'm taking it, so this is q, I can write this term as Q minus J. So it has all of the QJs except QJ. But I see because each of those are normalized, I can write the expectation of my notation is Q minus J. This should be Q minus J. Right? I can write an expectation of that. So my original cost function, which boils down to this, can be written as, if I only want to optimize Qj, I'm going to end up with two expectations. The first expectation and second expectation, but this expectation can be written as Qj log of the P tilde, and this is just an entropy. Yes.
Sorry, what was FJ again?
Huh?
FJ?
Fj was this term. So Qj is all of this ugly term, right? So remember that each of these Qj was proper probability. Okay. So I can still think of this as probability distribution that has all of the components except J. And I'm taking expectation with respect to this guy. This is why I wrote it as this. Expectation of inside for Q minus J. Make sense? Now, what I have is that if I fix all of the parameter constants, and I only want to optimize with respect to Qj, I'm going to have an expectation with respect to Qj, another expectation with respect to anybody else, Qj plus entropy. All right, so now the goal is that I assume the rest of them are fixed. I'm going to take expectation with respect to Qj. So now it's time to use calculus of variation. You remember the derivative of the entropy?
-1.
Yeah, exactly. So if I take a derivative of L with respect to Qj, it's going to give me some sort of like a minus log of the Qj plus 1. And this one is just a function, but you're taking expectation with respect to Qj. What do you think that the derivative of this term would be with respect to Qj? You're taking derivative with respect to Qj. What do you think that would be? It's very simple. It has a very simple expression.
Would be the expectation inside?
Yes, exactly. Because the linear term is as if that you are taking expectation with respect to AX. If you take the expectation with respect to X, you're going to get A. So you can think of expectation as a linear term. You can take it, so you can go home and apply the same rule, but you're going to get the same thing. So if you take expectation with Qj, you're going to get the term inside. Entropy, I worked it out for you at the beginning of the class. So what you are going to get, and set it to 0, is going to be term inside, and the entropy, the derivative of the entropy. Okay, right? So let me set that to 0. What I'm going to get is expectation of this guy by X. The reason that I said proportional, because I have to make sure that Qj is still proper density. And I didn't have any Lagrangian or anything to enforce it. This is why I just said that if I rearrange it, set it to 0, this one is actually not important because at the end it just shows up as a normalizer. So you have to normalize it anyway. So let's get rid of it. So all I have, so my form of update is going to look like this. And this is the update rule in mean field. The entire mean field is this update rule. If you are able to compute this expectation, which in many cases we can, you only need to exponentiate it, and you will have your Qj. And remember, P tilde J is easy. We didn't have the posterior, but we can, for unnormalized version, we have it. For any posterior, so if you want to estimate PZ given data, This is proportional to PZD. So your P tilde is this guy. And this comes from your model. It's easy, yeah.
So, like, you can here also see it as like valid data to have missing observation, right? And
Yeah,
the same
it doesn't matter. Missing observation is yet another unknown random variable. But the entire update rule of the mean field is you want to update your jth random variable, take an expectation of the log of the joint distribution, with respect to others, exponentially normalize. Okay. So in interest of time, I'm going to stop here because otherwise I have to rush the rest of it. Okay. Thank you.